Hello everyone, today we're going to be going over experiment 2, the reduction of 9-fluoronone. So this is a reduction reaction which is essentially increasing the amount of hydrogen bonded to a molecule or kind of decreasing the bonds to oxygen in a molecule. Same sort of idea. So what this reaction is, we start with 9-fluoronone, which is a ketone here. We'll add sodium borohydride, which is our reducing agent, and then we'll get out this corresponding secondary alcohol. So effectively what this reaction is, it's an addition of two hydrogens across this double bond. We'll add a hydrogen here and a hydrogen to the oxygen to make our alcohol. This reaction is really easy to monitor the progress of because our starting material is this bright yellow solid, and then we'll see a color change as the reaction proceeds, and we'll get a white solid as our product. So the mechanism for this reaction, we have this ketone here, so the oxygen is really electronegative. It'll kind of pull the electrons up towards it. This leaves the carbon here partially positive. That allows for this hydride to attack the carbonyl carbon. Note that it's the hydride and not the hydrogen. So this actually brings, the hydrogen actually brings its electrons with it. So we'll end up with this kind of BH3 as like its little byproduct. But in this step, we've just added a hydrogen to this carbonyl carbon. Now we have this oxygen with this negative charge. What's going to happen is really anything that can donate a proton. In our reaction, we add HCl, but it can also be just a solvent molecule. You can have ethanol or methanol donate a hydrogen to add to this oxygen here. That'll form our alcohol. So as you can see, we've effectively just added two hydrogens across what used to be this carbon-oxygen double bond to achieve our alcohol. And then a byproduct is BH3 and then sodium chloride as well. To work up the reaction, what you're going to do is you'll do a vacuum filtration with a little Hirsch funnel. You'll wash it with methanol. That's just to kind of get out any remaining ethanol as your solvent. And then for your analysis, we'll do melting point and IR. And then just a side note, whenever we're drying our product after we do the vacuum filtration in the oven, make sure that you only dry the product for 10 minutes. In the manual it says 20 to 30 minutes, but that's a bit too long, so we're just going to do it 5 to 10 minutes. The white solid will get kind of like flaky, and that's how you'll know that it's nice and dry.
So whenever we work in the lab, always use all the protective equipment, your goggles, gloves and lab coat, and your shoes must be toe covered. So now you are ready to go to the work in the lab. Let's start this reduction reaction now.
So these are both of our solid reagents that we're going to be using for this lab. We have 9-fluoronone. Notice the yellow color, like I said earlier. It does have this blue label because we have all of our hazards color-coded, so blue means health hazard. And then for sodium borohydride, pink or like red means it's flammable. Also do notice that we have sodium borohydride in this desiccator. That's because sodium borohydride is very hygroscopic and it will react with water in the atmosphere. So you can't just keep it in a jar like this. It needs to be sealed in its desiccator that will absorb all the water. So we're going to go ahead and measure out 200 milligrams of 9-fluoronone. So it's important, first we have to zero the scale. I'm going to turn it back on. Oh, there it goes. All right, so we're going to zero it out. Put our wayboat in there. And now we're going to tare. And then we're going to add 0.2 grams of the 9-fluoronone, or 200 milligrams. So we do have just a little bit too much, but it's not so far off. So we'll go ahead and keep this mass. So we have 213 milligrams. So we'll write that right here. 213 milligrams so we don't forget. Now we're going to weigh out 50 milligrams of the sodium borohydride. So once again, we need to make sure we zero first. And tare. So whenever you take off the lid of the desiccator, you want to slide it off. It does have grease on the lid, so it will be a little bit sticky, but once you get it to slide, you want to make sure you don't set it down face down like this, because the grease will pick up all of the junk right here. So you want to set it down just like this. So now we're going to grab our sodium borohydride and get 50 milligrams, 0.05 grams. So we did have a little bit of fluctuation, so we're just going to re-tare. Cool. So it shouldn't be much at all. Just going to grab a little bit. Try to tap it out. Notice it is hygroscopic, which means it'll be very sticky, so you're just going to have to dump it. So we got about half of what we need. So again, we did go just barely over, but it shouldn't be too much. So I'll go ahead and keep this mass, put this back in here, and then we're going to slide our desiccator lid back on. Awesome. So I'll go ahead and write down 59 milligrams for sodium borohydride, just so that we don't forget it. So these are our two masses for our two reactants. So next we'll go ahead and measure out the volume for ethanol for our solvent. So we normally keep all of our liquid reagents in the fume hood for y'all to measure out. So we're going to have them in here like this. It is important whenever you're getting your chemicals that you keep this hood right here below the sash height. So it says it right here. We need to make sure that it's at or below this line. So these are all of our liquid reagents we're going to use for this lab. Right now we just need ethanol. So we're going to go ahead and get 2.5 milliliters of ethanol. About just right at 2 right there. So now we're going to add half a mil. And that's good right there. So we're going to take this and we're going to use it as our solvent for our reaction. We'll be running the reaction in this 25 milliliter Erlenmeyer flask. Go ahead and pour this in here. So we're going to go ahead and add our reagents right now. This is our 9-fluorinone. I always like to bend the weigh boat so I can get a nice funnel going. Just kind of pour stuff in. Cool. Now we're going to add our stir bar. Turn on the stirring plate, and we're going to go ahead and clamp this down so that it doesn't move around. So next we're going to add our 50 milligrams of sodium borohydride. So like I said, this stuff is kind of sticky. So I'm going to go ahead and try to scrape out anything that doesn't just come out with this spatula here. go ahead and turn on the heat. Since we're aiming for around 55 to 60 degrees, we're gonna set it to double that, so right at like 120. Cool, that's good. So we'll leave it stirring with some heat, only for about 3 or 4 minutes. Once we get everything dissolved, we should see a color change from yellow to like kind of white, cloudy, clearish kind of a color.
This reaction is fast, and here you can see it changes the color within 2 minutes, and heat is still on.
Alright, so we've let it stir for about, it's been like 5 or 6 minutes now. So it's completely colorless, as you can see, so that means that all of the 9-fluorinone is out of solution. So now what we're going to do is start the workup part of this reaction. So we're going to go ahead and turn off the stirring, turn off the heat. We're going to unclamp it. Now it is a little bit hot, so we're just going to set it on this cork ring right here, turned upside down. Cool. So we're going to go ahead and take out this stir bar, and we'll add 2 milliliters of water, DI water. And we're gonna rinse the stir bar a little bit. Just to make sure we don't lose any product. And you see we get precipitation right there. So all that white stuff is our, that's our 9-hydroxyfluorine. So it's soluble in ethanol, but it's not soluble in water. So whenever we add water, we make some of it precipitate out. So this next part, we're going to allow it to cool down a little bit more. So we still have some excess sodium borohydride left in the solution, and we don't want that in here. So the next part, what we're going to do is we're going to take this reaction flask to the fume hood. We're going to add a little bit of 3 molar hydrochloric acid. That's going to react with the excess borohydride and cause it to kind of get rid of it as H2 gas. So we will see gas evolving, so that's why we're going to be doing it in the fume hood. So first we're just going to get a little bit more water just to finish out that precipitation. Cool. And in the manual it does say to stir with the micro spatula just to kind of help that precipitation occur, get the water kind of everywhere. So now this next step is we're going to be eliminating any kind of borohydride that's kind of trapped in this solid. So we'll go ahead and do this right now. You do want to be careful with the hydrochloric acid, as it is an acid and it will burn you. Just kind of add a couple drops. We do see bubbling. see the bubbling has kind of stopped now. So we're ready for the final step of the workup, which is the vacuum filtration. Before we do that, I'm going to grab 2 milliliters of methanol, go ahead and set it in the ice so that it's nice and cold for whenever we need it. So we got 2 milliliters of methanol. So what we can do with this is actually just take off this base part and set this directly into the ice. I want to make sure that it's nice and supported, but it doesn't tip over. Awesome. So we'll let that chill out for a while. Next, what we need to do is set up this vacuum filtration. So we'll lower our clamp down. We're going to go ahead and attach our vacuum. So it's probably closer. Oh. We're going to spin it around and attach our vacuum right here. Cool. So the vacuum filtration that we're going to be using is a Hirsch funnel. So this is called a Hirsch funnel adapter. It's just to make sure that we get a good seal into this kind of Erlenmeyer flask. So we'll go just like that. Cool. So now we're going to dump all of this stuff into our little funnel. All of the liquid and stuff should come out, and we'll just have our solid up at the top. So go ahead and turn this on for the vacuum. And then we can help get all that solid out with our spatula. Alright, so we're getting the last little bits out of the Erlenmeyer flask here. Cool. So we're going to go ahead and allow this vacuum to kind of suck dry. If you push down, you'll notice that we're actually get some liquid out. See there? So that just kind of helps the suction be a little bit stronger. We're going to let it suck dry for about 2-3 minutes. It helps if you kind of press out the solid. See there, we get a nice... All that stuff is probably mostly HCl, a little bit of water, and maybe some ethanol as well. So we're gonna want to make sure we press this dry. Once it's sat under vacuum for about another 2 more minutes, we'll add that 2 milliliters of cold methanol to really help it rinse. So we've gone ahead and let it air dry just under vacuum for around 2 or 3 minutes. So this is that last little step before we actually finish out for the actual measurement of our product. So we're just going to add this 2 mils of methanol just to get that last rinse. So according to the procedure, we're supposed to let it air dry after that rinse for 5 more minutes. So we'll check back in after 5 minutes and finish out this last part. So we've let it air dry for another 5 minutes. So we're going to go ahead and take it off the vacuum. Whenever you take something out of a vacuum filtration apparatus, first you remove the vacuum hose. Then you turn off the vacuum. Okay, in that order. So now we're going to go ahead and transfer our product onto this watch glass, which we've already weighed out. Just kind of scoop flip it out. So we're gonna set this into the oven. It's not gonna dry super efficiently like this, so we're gonna press it out a little bit, just to kind of help it dry once it's in the oven. So we'll leave this in the oven for about 10 minutes or so. So we're just gonna place our product right here in this bottom row. Leave it there for about 10 minutes and we'll come back and check on it and get a good mass.
So while our compound is drying, now it's time to remove all the dirty glasswares, and this is the another fun part of this lab, to clean all these glasswares nicely and dry it, and then return into the stock room so that it will be available for the next student. And while you are in the lab, don't remove all your PPEs. Please wear all the time.
So it's been about 10 or 15 minutes in the oven now. We need to make sure we grab our oven mitt. This is part of our PPE to ensure that we don't burn ourselves on the hot glass. So we're gonna go ahead and put this on. So our product here looks nice and dried out. Go ahead and grab it like this. Close the oven. So before we get a mass for this, we need to wait for the watch glass to cool down, or else it might be, we might get an inaccurate reading for the mass. So we're gonna go ahead and set this down outside and just let it cool down, and we'll record the mass once it's kind of cooled down. So we weighed the watch glass beforehand, before we even started the vacuum filtration. We got a mass of 35.422 grams. So we'll be subtracting that mass from the mass we get right here. Make sure that it's zeroed out. Go ahead and get this weight. $35.647. Awesome. So we'll go ahead and write that down. 35.647 grams. So to find the actual mass of our product, we'll take the difference of these two. So we'll get 522. So just over 225 milligrams. So the last part of our analysis is a melting point analysis. So we did this in OChem 1, but we're just going to go ahead and go over it for this experiment here. So we're going to kind of break up our product into nice small chunks. Cool, so that's probably good. So we're going to go ahead and grab one of our capillary tubes. And the best way to do this is you kind of want to shovel it in, kind of scoop it in like this. Might be easy to have like this here so that you can actually press it in. Once you get a little bit in, you want to tap it in. And then you want to scoop a couple more times just so that you get a good amount of product into your capillary tube. So once you get, a good amount, we're gonna go ahead and use an old burette to bounce all of this stuff down to the bottom. So the way we do that is hold this up here, and we're gonna drop it in at the top. That kind of helps force everything down to the bottom. Looks like it's mostly down there. We're gonna go one more time. So now that we got our sample ready, we're gonna go ahead and put it into our melting point station. Make sure it's plugged in. So we're gonna attach it to our lab quest right here. make sure that it is reading the output correctly. So we have this right at room temperature here. We can go ahead and turn it on so that it'll start warming up. And we're going to be watching through this window to make sure. We're just going to monitor it until it liquefies, and then record the temperature that happens at. So the literature value is around 150. So we're going to turn it up to around 180 just to kind of get it warming up really quickly. We'll slow it down once it approaches 145, 150, just so that we can actually get an accurate number for it. So we're at 145 right now. It is still steadily rising. I'm gonna turn it down just a little bit. So the melting point range is 153 to 154. That's the literature value. So we are approaching that. So I'm going to keep a close eye on it as it reaches this range. So it just started melting. It was at like 176. So it's a little bit higher than expected, quite a bit higher. I don't know if you're able to see this very well, but it is pretty much done, almost done melting by now. Yeah. So you'll go ahead and call it there. It was probably like 180, 181 where it really fully melted. So we have a somewhat broad melting point range and somewhat higher. So that kind of calls into question the purity of our product. Not to mention, if you look at our product, we do still have some yellow. We do still have some yellow in the product, and the product's supposed to be only white. So all of this kind of slight yellow that you see is unreacted 9-fluorinone. So that could be why we have that weird melting point range and it being so high. So whenever you're writing your lab report, these are all the required data points that you need. These will not be your data points. This is just what we had. So this is just an example. We'll actually give you data for each of these so you can do your own calculations. But just kind of to hit the important stuff, we got 225 milligrams of our product. Our theoretical yield was 215 milligrams. So that gives us a percent yield of over 100. So we'll talk about that here in just a second. And then like we just showed, our melting point was 176 to around 181. So the calculations that we need y'all to do here are just theoretical yield and percent yield. So if you don't know how to do these, I've shown a little sample here. So this will be different depending on what your data is. But for ours, we started with 213 milligrams of 9-fluorinone. You divide by the molecular weight of 9-fluorinone, then you get your mole conversion, and then you multiply by the molecular weight of 9-hydroxyfluorine. So whenever you do this multiplication and the division, you get 0.215 grams of 9-hydroxyfluorine. That's your theoretical yield. And then I just have 9F is 9-fluorinone, 9HF is 9-hydroxyfluorine. So, and then for the percent yield, it's actual over theoretical times 100. So we actually got 0.225, whereas our theoretical was 0.215. So divide those, multiply by 100, you get 104.65% yield. So a percent yield over 100% shouldn't really be possible. If you get something like that, it kind of calls into question the results of your experiment. So probably what happened here that caused the percent yield being high, we could have not left it in the oven long enough, so there could be still like excess liquid in the product. Another thing, like I mentioned, there was still unreacted 9-fluorinone in the product, so that might also be contributing some weight to the overall product. So both of those things could, attribute to the high yield. Lastly, for the conclusion, we just need a good description of the experiment in general. Talk about the percent yield that you calculate and sources of error, like I just mentioned, and then compare the melting point that we give you to the literature melting point value. And then we're also going to give you IR spectra of both the reactant and the product. Those will be on Canvas. We'll just need you to talk about kind of the differences between them and all the significant peaks.